we are now recording. Let's get the slideshow from the current slide. Here we go. All right, I think we led up to last time spanning sets. Now, remember what sort of the background here. We're talking about vectors in a vector space. These can actually be vectors directly line segments in subspace R2, R3, Rn, whatever. Okay. Or they could be vectors that are 2 by 2 matrices in the space of 2 by 2 matrices. Or they could be polynomials, or they could be functions, or they could be anything that fits within some other grouping. Okay. So if every vector in a vector space, whatever the vector is in vector spaces, can be written as a linear combination of vectors in some set S, then S is called a spanning set of that vector space. So what I was going to write that down, but I think it's all contained in the definition on page 171. So let's write it this way. Let me get my pen black. Okay. Let S, okay, now earlier V's were vector spaces, capital V's were vector spaces, little v's were V's. Now S's are spanning sets, so get used to this one. Let S be some set of vectors, V1, V2, V3, ... up to and including, is it N they use this? No, K, okay. Their counter varies, okay. Up to vector VK, okay. Let this be a subset of the vector space V, okay. The set S, okay, is called a spanning set. Okay. When, okay, these are the conditions. Every vector in V every vector in V can be written as a linear combination, okay, of the vectors in S. Okay. In such case, we say that S spans V. All right. Now, just a few things here. S is not the whole vector space V. It's a subset of that. Okay. But it's a spanning set when every vector that's in V, whether it's in S or not, every vector in V can be written as some linear combination of these vectors that are in S. Okay? Then we say that S is a spanning set, and the other way of saying that is S spans the vector space V.
I'd like to see how this works.
What's that?
I'd like to see how this works.
Okay. Let's one that you know already. Okay. You know I, J, K is the unit vectors for free space, right? All the space. Well, now certainly I, J, and K aren't all the vectors in the vector space. Okay. But you can do any vector you choose in here. You can say a linear combination of I, J, and K. So therefore, I, J, and K would be a spanning set for R3. It's a subset.
So basically, you can do anything to change those to make them fit.
Yeah, and when we say a linear combination, that's some C1, C2, C3 that add them together, and you can come up with every vector in V. Yeah. So now that's a classic simple example, but doesn't have to be that simple. You could have other things as well. Okay, so let's look at some examples of spanning sets. Example 4. I think what I'll do is clear this, but keep in mind what that definition is. Okay, here's a set S. It's a set of ordered triplets. Oh, guess which one that is? 1, 0, 0. 0, 1, 0. Huh?
It's been so long since
Yes, I know. And 0, 0, 1. I didn't know this was going to be the very first example, but it is. It spans R3. Okay? Because any vector and for some reason they're used now. And this vector, I'm going to write it in vector notation. I won't be consistent with it. U1, U2, U3. Those are the three components of that vector U. And this is in R3. Any vector in R3, okay, can be written as, this U could be written as U1 times, I shouldn't, these should be vectors up here too. I wrote them the way the book did. 1, 0, 0, huh? Those are vectors up there, and use a vector. But I should either use parentheses or vector notation. I haven't been consistent. Plus U2 times 0, 1, 0 plus U3 times 0, 0, 1. Okay? For some reason, this didn't write. Okay? All right. So, any vector U in R3 can be written as a linear combination of those three vectors. And since we chose them that way, 1, 0, 0, 0, 1, 0, 0, 0, 1, then the U1 is multiplied by I, U2 is multiplied by V, U3 is multiplied by, and that gives
makes perfect sense.
Yeah, yeah. And that's the classic example.
Whatever your first thing is for the first vector, U1 times
Yeah.
1 is that, plus the second one plus the third one.
All right. Now,
Too bad they're not all that easy.
very much so. Okay. Let's see. I think we can actually get this one on here. This is the A one. Let's try to get B on here too. Here's a set, S. But this is now not a set of vectors as we think of it, but as polynomials. 1, x, and x squared. Okay? This spans the space we call P3, and if you recall, I'm sorry, P2, yeah. P2, if you recall what that is a set of all polynomials of degree 2 or less. Not all second degree polynomials, but all polynomials of degree 2 or less. What's that?
It's even more than just the second degree.
Right, exactly. Because any polynomial function p of x, okay, that's little p of x, a second degree or less would be, say, ax squared plus bx plus c. That's your standard definition for it, except they do it exactly backwards from this, which sort of aggravates the fool out of me. That's sort of standard form, but they wrote it the other way, so let me write it the way they do. Okay. Writing it that way. So any polynomial in P2 that's degree 2 or less can be written as a linear combination A times this vector, think of that as a vector now, polynomial, B times that one, C times that one. Yeah, any polynomial, why not AX plus CX squared plus BX plus A can be written as a linear combination. Also, it's the same type principle as before. These are sort of your simplest. I keep wanting to use the word we're going to introduce later, and we haven't yet. Your simplest fundamental set that could be. Okay, we'll give it a different name later. Okay. Oh, and here they do it actually. These are called standard spanning set. Those aren't your only ones, but these are the standard. They're the simplest ones. The building blocks, you can build anyone into it just by doing just like we did here. Standard spanning sets of R3 or P2. Okay? A and B there. Okay. And we'll learn more about standard spanning sets in the next section. We'll actually give them a slightly different name. Okay? So let's look at example 5. And we'll look at another spanning set that's not a standard. Show that this set, S, is a set of, and this time I will try to put it in this, 1, 2, 3. There's a vector in R3. 0, 1, 2. A vector in R3. And negative 2, 0, 1. Another vector in R3. Show that that set also spans R3. Okay? Well, we start off similar to what we did before. Let U be some vector in R3, and we'll express this as U1, U2, U3. Okay? It's a vector in R3. Be any vector in R3. Okay? Not any particular one, any one, whatever. So what we need to find then is a C1, C2, and C3 such that C1 times 1, 2, 3 plus C2 times 0, 1, 2 plus C3 times negative 2, 0, 1 is equal to U. Okay? So that any, you need to find the C1, C2, and C3 such that that U, which is U1, U2, U3. Okay, sorry, it ran out of room. Okay. Any vector U can be written as that linear combination. Okay. Now, hopefully you see that this would require U1 to be C1 minus 2C2, 3. See that? Right. C1 from here, the first entry there, U1, is C1 plus 0, C2 plus minus 2, C3.
Okay, yeah, all right.
Okay. And U2.
So U2 would be 2C2
2C1.
plus C2.
Right. Done. U3 is equal to 3C1
plus 2C2.
wait, okay, plus 2C2 plus C3. All right. Now, all right. Now, what you do then is set this up as a matrix. 1, 0, minus 2. Yeah. And this will be our U1. Okay. Goodness gracious, this aggravates me. 2, 1, 0, U2, and 3, 2, 1, U3. Okay? Now, it doesn't matter what the U's are, so don't worry about that. But we do our row reduction and see what happens. What would that be? One thing that makes it kind of special is the diagonals are all ones, but without everything else being zeros or this being reflected across there, that would be symmetric.
I don't know. It's reflected across the non-dominant.
Oh,
diagonal.
oh, I see. Yeah, you're right. Yeah, it is. But yeah,
I just thought it was. I thought it was different.
Yeah. Yeah.
Wonder if that'll have anything happen.
Yeah. Let's see, if we did the transpose of that, it would just flip everything that way. It wouldn't flip it the other way. So no, I don't think it is interesting. It is, but I don't know if that tells you anything. But what would we do here?
No, that would make it. Across the dominant axis if you did.
Across the dominant, yeah. But this is the non-dominant.
I'm talking about if you did the transpose, then it would be symmetric by the dominant axis.
Would it?
Yeah, it'd be 1, 2, 3, and 0, 1, 2.
Yeah.
Then negative 2, 0, 1. So
Mm-hmm.
1's on the diagonal.
Right.
0s and 2s, and then negative 2 and positive 3.
Okay. That would. So, except, yeah. I mean, that part would. What would you do with the U's then?
Yeah.
That's
the
issue
question.
there. And would it matter any? But I don't know. But let's do what we need to do here. What would that be? Yeah.
Be negative 2 row 1 plus row 2.
Okay, it's not writing. Goodness, why did it do that? It's trying to stop.
Well, I have the matrix written down, so
Okay.
you can just go ahead and discard it, I guess. Or you can keep it, but you won't be able to erase it.
Yeah, but keeping it is going to try to store this.
Exactly, that's what I'm saying. You can't keep it.
Yeah. So, what a pain in the neck. Okay. Let me write that matrix down again. Oh, no, I got to go back and change this. What a pain.
Matrix is
Okay.
1, 0, negative 2.
I'm going to do it like you did.
1, 2, 3.
Yeah.
0, 1, 2. Negative 2, 0, 1. And U1, U2, U3.
Okay. And we're going to do a minus 2 row 1 plus row 2 is the new row 2. So this would be,
Go ahead and do row 3 as well.
yeah,
Negative 3, row 3 plus
row 1.
Row 1 plus row 3.
Yeah. Okay. So we keep row 1, 1, 0, negative 2, U1. This would become,
0,
okay,
1,
1,
negative 4.
not negative 4, would it be? 4, yeah. Ooh, that's an ugly 4. The pen is just, it's slow, and then it decides to write wherever it wants to. Okay, 4, okay. And then this will be a negative 2 U1 plus U2. Okay.
I was worried.
All right. This will be a 0, 2, 7. And this will be a minus 3 U1 plus U3. Okay.
This is only going to take up tons of space.
Now, all we have to do is get it into row echelon form. We don't need it reduced. Yeah. So this will be negative 2, row 2 plus row 3. We're going to need some room for that last one, but that will be 1, 0, negative 2 U1, 0, 1, 4, negative 2 U1 plus U2. And this will be a 0,
Sorry, I'm trying to catch up.
yeah. I will just let you catch up. Negative 1. And this will be, this will be a 4U1 minus 2U2 plus, or minus 3U1 plus U3. Okay? If you add all those together, that gives you U1 minus 2U2 plus U3. What's that? Write something up.
No, I think
Okay.
for some reason I wrote a 4 somewhere it wasn't supposed to be.
Okay, it may have been my U looked like a 4 or something. I don't know. Okay, so anyway, to simplify this just a tad, that would just be a 1U1 minus 2U2 plus 3 plus U3. Okay. Now, we could negate the bottom, but who cares? We see that C3, which is what this stands for, C3 is equal to negative U1 plus 2U2 minus U3. So for any U, you got that one, and then you can back substitute and get the other. And it doesn't matter what, these are linearly independent, you know, 3 distinctly different values for your C's. Okay?
So we don't have to solve for each C?
If this were a test or something, you probably need to write out what each one of those are, but you see, you can get there. The key is you didn't wind up with a row of zeros here.
Right.
Or even worse, zeros here and a non-zero there. That would have been no solution. All zeros would have meant you have an infinite number of solutions, so they wouldn't have, they wouldn't have been linearly independent. The zeros and then something that's not zero would say it can't happen, period. Otherwise, it says there's an infinite number, they're not linearly independent. This tells you they're linearly independent. The C's are. The C3 would be this thing, the C2 would be this thing minus 4 times that, whatever that turned out to be. And, so yeah, you could go back and do it, but the thing is, they're arbitrary. I mean, they have unique values, and whatever U1, U2, and U3 you put in there, you get what those C's are. And There's no way around them. So, yeah, they're a linearly independent set because this came out to be a with no zero rows and no zero rows equals something that's not zero. Okay, that's not allowed. Okay. The coefficient matrix of this system is a non-zero determinant. That's the other thing you could have done. Rather than done row reduction, all you had to show was the determinant is non-zero. Let's do the determinant then. Which one would you like to do? Up to the original. Forget about the U1s, U2s, and U3s.
I'd say let's do the bottom.
Oh, you mean come down here and do it?
Or
Why not?
We
Yeah.
can, yeah.
Okay. What would be its determinant?
I would say let's do the left column, right? And that would be positive, negative, positive. Okay, so that'd be -1.
-1, exactly.
Boom, done.
For some reason, I was looking at this and that would be a -1. So yeah, either one would be the same thing. So yeah, it's not zero. That's all you need to do. Now, we didn't have to go through these steps, but if we had started with just that one up there, we either use the first row, the third column, the second row, or the second column.
I wonder why they use the transpose of it. Symmetric matrix.
Yeah,
I don't know.
yeah,
It's kind of weird.
yeah, it is a little strange.
Kind of makes me think there's something you could do that would.
Well, it may be that a transposable, well, I mean, any matrix could be transposable, but if a transposable matrix is symmetric, then that guarantees it to be non-singular. I don't know. It would seem like that would kind of make sense, okay? But rather than row reduction, which we did, they just did a determinant without doing any row reduction. All right, now let's look at example 6. From example 3, which is on the previous page, we know that the set S equal, this is a subset of 3 space. It looks pretty similar, 1, 2, 3. Now, writing them in parentheses again, sorry. 0, 1, 2.
And these are vectors, right?
These are vectors, sorry. And -1, 0, 1. Now, the only thing that changed there from our previous example was the previous example was -2, 0, 1. This is -1, 0, 1. Okay? And it says, does that set span R3?
Set up an equation and find out.
Okay?
So
Now, notice what we did last time. Yeah, okay. Let's do a U1, U2, U3, and that would be a U. You're right, that's vector U, okay? That's equal to C1 times 1, 2, 3 plus C2 times 0, 1, 2 plus C3 times -1, 0, 1. Okay, and let's see what we get. U1 equal C1 minus C3, right? U2 is equal to 2C1 plus C2 plus C2, right? Okay. And U3 is equal to C1.
3C1.
Yeah, I'm sorry, 3C1 plus 2C2 plus C3. Okay. And all right. So we set those up as a 1, 0, minus 1. 2, 1, 0. I don't know why it's not writing. 3, 2, 1. Right? Now, notice, let's scratch our former supposition. This is also the transpose of a symmetric matrix. And this one ain't going to work. We know that already. Yeah. You can choose any, let's do the way they did, determinant. That might be a little easier. You choose any row, any column. Which you want to go with? First row makes perfect sense. And the determinant of this would be 1 times 1. Okay. Minus 1 times 4 minus 3, which is 1. Yeah. Okay. Be 1 minus 1 equals 0. And this isn't going to, that's not a singular matrix, so therefore it cannot produce a linear combination. Cannot.
So always check the determinant before you go through and put it in
Right. Unless the determinant's going to take you more time to do than another method. But remember, we had those, what was it, up to 6 or 7 conditions. If any one of them meets, then you have a reduced transposable matrix, inverse matrix, matrix that has an inverse, in other words, a non-singular matrix. In these, it just happens to be because you got the zeros in there, it's real easy to do the determinant. Others, it might be easier to do a row reduction or something else. So this one will not. Because if you were to try, now what they cheated on, they say go back to example 3 and you found out here is a vector W that happens to be in R3, but it can't be written as a linear combination of those, so therefore it isn't a spanning set. Okay, those vectors don't span.
That's kind of like you pulled this vector out of a hat and it doesn't work.
Right. Well, it was a selected hat, one that we had done before. Okay, but it is an R3. Okay. Comparing the set of vectors in example 5 and 6, note that the sets are the same except for a seemingly insignificant difference in that third vector. But if you were to plot these, which I don't trust my plotting at all, but if you do check this and keep up with where you are, see number, for example 5, those 3 vectors define, cover all the space, okay? So they span it. Whereas the next 3 vectors, 1, 2, 3, 0, 1, 2, and negative 1, 0, 1, and just a little hint here. Notice something here, okay? Reduce this by 1, reduce this by 1, reduce that by 1. These are coplanar. You've done the same thing to every vector in there to produce one of the others. So that, whereas when you add a minus 2 here, you can't do that. So this happens to be those 3 vectors, and they show it in the text.
They're all on a plane.
They're all on a plane. And that plane includes, there's a bunch of vectors outside that plane that are in R3 that are not in the plane, so therefore it can't span it.
So,
Whereas the other, these two made a plane, these two made a plane, and some linear combination of those planes, you cover everything
right.
in the whole
So
space.
you have just the one plane.
Right.
You can do anything on the inside of that plane.
Right.
Nothing else.
But you can't get
add
anything
a
outside
vector
of it.
that goes outside. You can swing
Then
it
it
all
expands.
around.
Exactly. Right. All right. That's a good concept of what spanning is. Okay. Now,
This isn't.
okay. They called this one S2 on the next page. I don't think they called it S2 on the previous page, but they called the S2 on the next page, page 172. That was the example 6 set. Example 6 set, okay? And the thing is that spans a plane, okay? Now, it doesn't span the whole set. We found one vector it wasn't, but or they found one. All right, although the set S2 does not span all of R3, it does span a subspace of R3, namely the plane in which the three vectors of S2 lie. That subspace is called the span of S2 as indicated in the next definition. Excuse me, I got hiccups. So let's do that next definition. If S, and this is a set of vectors, V1, V2, V3, comma, dot, dot, dot. Are we still VK? All right. Is a set of vectors in a vector space V, okay, then the span of S, okay, what S spans is the set of all linear combinations of the vector in S. Is set of all linear combinations of S in V. They don't say the NVs. Probably I'll take that out just to keep you from thinking that spanning V. It doesn't. Okay. But it is in V, of course. It's a subset of V. All right. So what that's saying is the span of S of this set yuck. All right. Span of S is equal to the set of all possible linear combinations C1, V1 plus C2, V2 plus C3, V3 plus dot, dot, dot plus C sub K, V sub K. Okay? Set of all those, and these, of course, the C1, C2, C3, dot, 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 up to and including C sub K are real numbers. Okay, in other words, you can't have complex numbers in there. Okay? The span of S is denoted by and that same is denoted by that.
So
No, the span of a set, which spans something. You know, yeah. Yeah, like I said, this gets circular after a while, or it feels like it. You could call it the span of, and rather than saying the set S, the span of the set. V1, second. Yes, exactly. Okay. All right. Now, when the span of S that space that set spans, okay, happens to be V, this is capital S here, okay, then we say that V is spanned by that set of vectors. Then V spanned, I don't have it right. That set of vectors, okay, or that S spans V, okay, blah, 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 circular, circular, circular. The following theorem tells you that the span of any finite non-empty set of a vector space is a subspace of V. So they say this is what it's telling you, and then it tells you. Why have both of those sentences in there? Just get to it, okay? So here's theorem 4.7. The span of S is a subspace of V. If S is this set of vectors, V1, V2, V3, dot, 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 up to, still K? Good, okay? Is a set of vectors, and this is redundant too. That's obviously a set of vectors. That's why you write it that way. Is a set of vectors, okay? Yeah. In the vector space V, vector space V, then the span of S, okay, if S is this, is a set of vectors in the vector space V, then the span of S is a subspace of V. Now,
It's probably
the only thing I have a little bit of a, oh yeah, okay, got it. I was going to say, can you guarantee the zero vector is in this? Because that is required for it to be a subspace. It can be a subset, but can it be a subspace? You have to have the zero vector.
well,
Yeah. If all of the C's were zero, that guarantees it. And remember, the C's can be any real numbers. So yes, that guarantees that the zero vector is in there.
And I bet you this is German-based math because K or constant is
Yeah.
called the K in German.
Right. Wouldn't be surprised if that's not where it came from. I'm trying to think of the dudes that did this kind of stuff, if any of them had German names, but we'll see.
But yeah, it's similar to the way we spell it, but it starts with K.
Right. And then, moreover, in addition to that, the span of S, okay, the span of S is the smallest subspace of V, okay, that contains S. Okay. in the sense that every other subspace of V that contains S must contain the span of S. Now this, again, almost seems like it's circular here.
And they got a proof afterwards.
Yes.
The proof might be more helpful.
That contains S in the sense, okay, the writing is terrible, that every other subspace of V that contains S must contain the span of S. Okay. Again, that almost seems like you're going nuts with spinning the wheels here. But say here we have a set with k vectors in it. It's a set of vectors in the vector space V. Its span, that implies the span of S is a subspace of V. We talked about that because it would contain the zero vector, and it therefore it's a subset of it, contains a zero vector. All the rules work for it. So yeah, the span of S is the smallest subspace of V that contains S. Okay, the span of S is the smallest subset. That means that minimum number of these vectors that will comprise all of this subspace, that's the span of S, okay? You could have other vectors thrown in there, but some of them are going to reduce to zero, okay? What you have left is the smallest that you do. In the sense that every other subspace of V that contains S must also contain the span of S. Because certainly, if it's a subspace of V that contains this set of vectors, it has also contained the span of that set of vectors, the smallest number that it can do. So yeah, it almost feels like it's going in circles, but they are really making. Now, like you said, there's a proof here, and it looks like they almost start stuttering here. Okay. To show that the span of S, the set of all linear combinations of V1 through Vk is a subspace, show that it is closed under addition and scalar multiplication. And I like also to say that it contains a zero vector, okay, because just the other two don't always.
Well, if scalar multiplication works.
Yeah. Right. Closed under scalar multiplication, yeah. If C was zero, yeah, that would have to contain it, okay. So yeah, it does include that, okay. So let's consider any two vectors, U and V, that are in the span of S, okay? Not just in S, but in the span of S, the smallest set that you have of those vectors that defines all that, okay? And we'll name them. Sorry. U, and sort of irritates me they use V when they had the original things being V. Why couldn't they use a W, okay, just to keep you from, but it's okay. U is C1 V1 plus C2 V2. I like that. V is D1 V1 plus DV2. So they are both of those are made up of the vectors in S, okay? And they're in the span of S, okay? Now, all those are scalar numbers. U plus V, if you added those together, you add the constants and keep the thing, and those constants are real numbers because both parts are real numbers, yeah. So yeah, scalar addition vector addition works. Scalar multiplication, and again, if they're going to use C, why didn't they use D1 and E1 up above? Why did they have to use C there too? But just remember, they are not related, even though they look the same, but they're not. Then this is also in the span of S.
So I mean, it works.
Yeah, and that's it. It's just those two things work, so therefore it covers it. So let's go back now to linear dependence and linear independence. All right. Start over on a clean page if I can get it to come up. How are we doing on time?
We got about 10 minutes.
Oh, okay.
And the whole C equals 0, that's trivial solution.
Right. Okay.
That's the 0 vector, right?
Right. Got it. For a given set of vectors, S, this is just some set of vectors, S, and here they are, V1, V2, V3, ... up to and including V sub k, the German k. Yep, still using it. In a vector space, these are elements of the vector space V. Okay. For that set of vectors, the vector equation C1 V1 plus C2 V2 plus C3 V3 plus ... plus C sub k V sub k equals 0, and that's a 0 vector because it's some of those, always has the trivial solution, for sure. When C1 equals C2 equals C3 equals C, where is the, there it is. This is aggravating. Okay. Just had gotten to equal ... equal C sub k, and all those are equal to 0. Certainly that makes that true, if all those are. Okay. That linear combination always has a trivial solution. Often, however, there's also non-trivial solutions, and way back in example 1a, you saw a set that gave you a non-trivial solution, okay, where your C1, C2, and C3 were not all zeros, okay. I'm not sure why they're doing this, but let's do it. Here's your set of vectors, and this time rather than having it generic, we're going to have it specific. Okay, 1, 3, 1, 0, 1, 2, and 1, 0, negative 5. Okay. That's certainly, man, I'm getting cold. It's certainly a set in R3, okay? 3 vectors in R3, okay? We'll call them V1, V2, and V3, okay? Now, they note here that V1 can be written as a linear combination of the other two. I would say it's going to have a V3 in it, right? Because that will give you a 1 here. And 3 times V2 okay. And let's see if the rest works. V3 would be minus 5 plus 6 would be a plus 1. Yeah, so that certainly works. Okay. Now, do you think this spans R3? Well, if you chose C1 to be 1, C2 to be minus 3, and C3 to be minus 1, then this would be the 0 vector without the C's being the trivial solution. So you have more than one combination there. So this, in other words, let's say V3 going here, 2 times V2 here, V1 is a combination of those. They're all in the same plane. So it can't span all of space, R3. Okay. Okay. So the vector equation, like I said before, C1 V1 plus C2 V2 plus C3 V3 equal the 0 vector. For that to span it, the only way that could do it would be the trivial solution. Since this has a solution not the trivial solution, such as C1 equal 1, C2 equal negative 1, and C3 equal negative 3, then that's not the trivial solution, and yet that gives you the 0 vector. It can't do it. It has a non-trivial solution in which the coefficients are not all 0. I mean, you can just have one not being 0, or just a couple. Most of them, yeah.
I think C2 and C3 are switched.
What's that?
I think C2 and C3 are switched.
Oh, yeah, I'm sorry. Yeah, I'm sorry. Okay, sorry about that. Okay. This characteristic is described by saying that set S is linearly dependent. Had the only solution been the trivial one, C1 equals C2 equals C3 equals 0, then the set S would have been linearly independent. This concept is essential to the study of linear algebra, formally stated by the next definition. Do we have time to state it? A minute? Okay, I think we can. Set of vectors. Set of vectors, writing them as one word, S, which is the set of V1, V2, V3, dot, 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 still going up to V, okay? Okay. In a vector space, okay, is linearly independent when the vector equation C1 V1 plus C2 V2 plus C3 V3 plus dot 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 plus C sub K V sub K equals 0 equals the zero vector has only the trivial solution. Then it's linearly independent. Okay? And that trivial solution would be C1 equals C2 equals C3 equal dot 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 equal C sub K, and they're all equal to the number 0. If there are non-trivial solutions, at least one, just one, any one, then linearly dependent. Okay. And we'll pick up with example 7 next time.
We made pretty good progress.
Yeah, we did okay today, even with a late start.
I don't know what it is. I guess differential equations, just because there's so much explaining to be done
Right.
to do anything.
Yeah. Okay. You want my key?
Sure.
Okay. If you'll flip that on the way out.
Don't forget to stop screencast.
The what?
Screencast.
Yeah, that's what I'm going to do now, and I'm going to try to get some of these